Okay, today's lesson, we're going to be looking at solubility rules for solutions, and I have a small assignment to do at the end of today's lesson that you're going to be handing in to me as well. So we're going to roll through this one fairly quickly. On the screen, I usually do this as a demo in class, but unfortunately that's not an option. Okay, so what I have here is a saturated solution of sodium acetate. Sodium Na, acetate is CH3COO minus. So NaCH3COO. It's an ionic compound, dissolves in water, has pretty good solubility. So my first question for you is, what makes this solution saturated empirically? Empirically means observing it. So when you look at it, how do you know it's saturated? Just by looking at it. What does saturated mean in order to be able to understand that description? And then secondly, theoretically, what defines this solution as saturated? So in theory, why is it saturated, and what does it look like as a saturated solution? So that's where we're going to go today. Now I want to show you a little video first of all. This solution actually started out super saturated. So there's another term. What does that mean? Super saturated. I'm going to show you how it transitioned from super saturated to saturated. So this is the demo I usually show in class, but we're going to have to watch it on YouTube today. Okay, here we go. So watch carefully.
Just really quick, I'm going to add one tiny seed crystal. I'm not sure if you can see on the tip of that scoop over there. All right, the tip, I'm going to add that to my super. Okay. Just really quick, I'm going to add one tiny seed crystal. I'm not sure if you can see on the tip of that scoop over there. All right, the tip, I'm going to add that to my supersaturated solution of sodium acetate. And we will see it go from a supersaturated state to a saturated state in just a few seconds. Isn't that cool? So we see that the sodium and acetate ions recognize the crystalline structure of that seed crystal I just added, and they add to it, and we form one big crystal. And when I tilt this to the side, you can see it looks like a big chunk of ice, doesn't it? So now we're back. There's a little bit of water in there. You might be able to see it. We're back to our saturated state right now. So we've gone from supersaturated to saturated in just a couple of seconds. All right. Hope you like that. Bye-bye.
Okay, so that was supersaturated turning into what you see here, saturated. So what's going on? How does all of this work? Okay, well, in your notes, we've got some vocab to fill in. Super slow. Let's go. There we go. Okay, so let's take a look at this graph first of all. So that solution that you saw was supersaturated. That's up in this region of the graph. So let's say that it was somewhere up, was at room temperature, so it's probably sitting about here. So the idea behind saturated, or this line, is saturated represents the amount of solvent, or let's say even the amount of solute that dissolves in the solvent at a given temp. So messy. It's terribly slow. Okay, so let's say at 20 to 23 degrees Celsius in a saturated solution, you should have about 50, 60, 70, about 80 grams dissolving. That would be full or saturated. If I had 50 grams, it would be unsaturated, unfull. So the most solute that I can dissolve at 20, what are those, 5? So that's probably about 15 degrees Celsius. At 15 degrees Celsius, if I have 50 grams dissolved, I'm unsaturated. If I have 80 grams, I'm full, I'm saturated, no more can dissolve. What if I've managed to dissolve 250? That's way more than you would normally be able to have. We describe that as a supersaturated solution. Now, in that video, what he did is he added a little crystal. He disturbed the system and caused it to jump from supersaturated to saturated. So where did that? So we had 250, 150. I got to put my reading glasses on. 150 down to 80. So that was 70 grams of solid that literally jumped out of solution as a solid, and we were only left with 80 grams at that temperature. So that's why it turned into what looked like solid ice crystals. That was 70 grams of sodium acetate leaping out of the supersaturated solution, getting it back to its saturated state. Now you might be wondering, okay, well, how did he get that supersaturated solution? To make it, he simply heated the solution up to here. So he took it to about 110, 120, about 110 degrees Celsius. Because at 110 degrees Celsius, if you look across, you can fit 150 grams. So you heat it up, get the solute to dissolve, and then you slowly, gently cool it down to 15 degrees Celsius. And then at that point, it's super saturated, very unstable, and just this tiniest little disturbance and all of that excess solute that's dissolved will jump out. So that's the theory behind that supersaturated solution, and this is the vocabulary we're going to be using today. Okay, so in your notes, you have a few things to fill in. Solubility refers to the concentration of a saturated solution at a given temperature. So this is a solubility graph. We're going to take a look at this. You have it in your notes as well. I was doing some research today, and there's some debate. They think this line is an error, so we're going to ignore it. The cerium sulfate, pretend it's not there. Okay, so first question, what trends do you see? When you look at this graph, are there any trends or patterns? And you should see the following as temperature increases. So as temperature increases, what happens to the solubility or the concentration of solute in solvent? The solubility increases. So as a general rule, you're seeing this kind of a trend. As we move across in temperature, the solubility increases. Temperature is getting higher, solubility is getting higher. Now there's different rates in here. You can see here's a really steep one. KNO3 has a huge increase in solubility with temperature. And something like sodium chloride right here has a very slow increase in solubility with temperature. So those would be your two extremes. And then the question, so this one, which compound is most influenced by temperature? That would be the KNO3. And then least influenced would be the NaCl. Now let's jump back to this one. Any exceptions to the trend? Any anomalies? There is one. If we ignore the cerium, there's one. So I'm going to put it in blue. In case you haven't spotted it, NH3. NH3, the solubility decreases as temp increases. So why is that? Well, the trick here is this graph doesn't have states. NH3 is actually a gas, and everything else in here is a solid ionic compound. So these are all ionic compounds which increase solubility with increase in temp. Ammonia is a molecular gas or a molecular compound, and that's why it is the opposite. Okay, and we'll go through that in detail today. So you should be able to look at a solubility curve, look at trends, explain what's going on, the effect of temperature on grams of solute that will dissolve or solubility. Okay, so into our notes. Here we go. In general, solids have a higher solubility in water at a higher temperature. In other words, the solubility is directly proportional. Directly proportional to the temperature. So what that means is as temperature increases, solubility increases. Arrows are in the same direction. 2 thumbs up, directly proportional. Okay, so let's look at some scenarios here. We've got 3 beakers with NaCl. So these little dots that you see, let's go to a different color. These little dots are Na plus and Cl minus ions that have dissolved. Okay, so this is what it looks like when it's dissolved. So the first question is, which of these beakers is saturated? And how would you know? Just by looking at it. So how do we know it's full, that no more solute can dissolve? When there's a pile of solid NaCl. That's telling us we can't fit any more. If we add more, it just keeps piling up on the bottom. So this is our saturated solution. The other two are unsaturated. They're unfull. We can still dissolve more. Okay, next question. Which beaker is most likely at the highest temperature? So remember with these ionic compounds like NaCl, as temperature increases, solubility increases. So which one has a higher solubility, has more grams dissolved? And that would be, let's see, that would be our hot beaker, and this would be our cold beaker with less solute dissolved than the hot one, more solute dissolved. More solute dissolved. Okay, makes sense? Now this rule only applies for, that's so messy, I'm sorry. So only applies for ionic compounds. Okay. Gases. Gases have a higher solubility at lower temperatures. Whoa, that's the opposite. Okay, so that means that solubility of gases is, do you know the word for opposite? So there's directly proportional and inversely proportional. So as temperature increases, solubility decreases. Temperature increases, solubility decreases, inversely proportional. Gases have a, let's move on to the next one. So now let's look at pressure. Gases have a higher solubility at a higher pressure. So as pressure increases, solubility increases. So what word am I putting in here? Directly proportional or inversely proportional? D-I-R-E, that is so messy, directly proportional. Okay. So let's look at some examples here. When you take a glass of pop, which has carbon dioxide gas dissolved in it, and you pour it into a glass, you always add ice. Not always, but you should add ice. How does ice affect the solubility of carbon dioxide? Why do we add ice? So we know that the decreased temperature will increase the solubility of the CO2. In other words, the pop will stay fizzy longer if it's cold because the carbon dioxide gas will stay in the cold water or the cold pop. If you leave that glass out at room temperature where it can warm up, will there be more or less or the same amount of CO2 dissolved as the pop warms? correct answer would be less, because of that inversely proportional rule. As it heats up, the amount of gas will decrease. Your pop goes flat. Okay, looking at this is our gas dissolved in water, and this would be considered low pressure. If we push down on the piston and increase the pressure, we're adding more. These are all new gas molecules that have dissolved. So more gas molecules are soluble at higher pressure. Okay, so you can squeeze more in. So how does this work with a can of pop? Well, when they put the carbon dioxide gas into the pop, it's put in at high pressure. So when they can it, they put it under high pressure. When you open the pop, you are lowering the pressure. You're letting the gas out, and it will leave because it's lower pressure. So let's see if you can answer this question. If you carbonate pop at sea level, where we have high pressure, this is so slow and messy. Okay, so if you create the pop at sea level under high pressure, and then you go up in a plane where you have low pressure, what happens when you open the pop? So it started at high pressure, sealed. You take it up well above sea level where you have low pressure, and then you open the pop. Will more or less CO2 come out? If you've ever been on a plane and seen this, when the stewards or stewardesses open a bottle of pop, it's a crazy amount of fizzing that goes on as all of the CO2 gas comes out because the pressure is so low at high elevation. So low pressure, low amount dissolves. That's part of the reason as well you don't see many fish in really, really high elevation lakes, because there's very little oxygen gas in the water dissolved for them to breathe. Okay, some more vocabulary terms for you. Immiscible. Immiscible means it does not dissolve in water, forms a separate layer. So for example, oil and gasoline are immiscible in water, they do not dissolve. Miscible are things that dissolve completely in water in any proportion. You could take 1 milliliter of water, and you could add 1,000 liters of ethanol, and it would dissolve in a milliliter of water. They will mix in any proportion. Okay, so we say that polar solutes like ethanol, like the alcohols, are miscible in water in any proportion. And it all has to do with polarity. Okay, polarity, polarity, polarity. And it's that hydrogen bonding of water that allows other polar molecules to dissolve, or other things with hydrogen bonding. Okay, so the rule is liquids can be miscible or immiscible, and its non-polar substances are immiscible. They do not dissolve in water, whereas polar substances do. And the rule, the very simple rule, is like, oh my gosh, this is painful, this thing. Like dissolves like. So if you are polar, you will dissolve in polar. If you are non-polar, you will dissolve in non-polar. An example of that would be if you have grease on your hands, which is non-polar, it's like oil, you cannot get it off with water. An easy way to get it off would be to use gasoline, because gasoline is also non-polar, but then your hands are going to smell like gasoline, so nobody does that. But mechanics will often take greasy tools and clean them with a solvent like gasoline, which takes all the grease off. So polar substances dissolve polar, non-polar substances dissolve non-polar. And it says here, polar substances tend to increase their solubility with an increase in temperature. Why is that? It just has to do with collisions. If things are hot and banging into each other, it's more likely that the water molecules will collide when they're hot, moving around fast. They'll have more collisions and interact more with the solute and cause it to dissolve. If it's a crystal, they'll break the crystal apart into ions. And if it's a molecule, they're just better at surrounding the molecule and dissolving it at high temp. Elements have low solubility in water. That's just a fact. Okay, they keep their elemental state. So for example, if we put fluorine gas in water, it tends to stay as fluorine gas. If I put solid gold in water, it stays as a gold. If I put mercury liquid, it stays as mercury liquid. That should be an S, solid. Okay, so elements always keep their state in water. Carbon is useful as a filter for removing organic compounds because carbon is considered organic. So any compounds that have an odor that are found in water can be removed with carbon because it attracts organic materials and organic odors from the water and absorbs them. So that's why a lot of filters are made of carbon. It doesn't dissolve, and it's good at removing other organic components. There are some exceptions to the insolubility rule for elements. The halogens and oxygen are slightly soluble. That's good news for fish because they need that access to oxygen to survive. And the halogens are really reactive, so they also have an important role to play in our aquatic ecosystems. So those are the exceptions to the rule. And I think we're done all the notes. So now we're going to move to your activity for the day. Something a little different. So what we're going to be doing is building a graph, and you have this data in your notes. So I'm going to get you started on the graph, and then to finish the lesson, you're going to do the rest of the graph on your own. How does it look like? Okay, so the data that you have is 4 different temperatures of water, and you are dissolving potassium nitrate until it's saturated. So the question is, what mass of potassium nitrate will dissolve in water at various temperatures? So the way you figure it out is you dissolve potassium nitrate into the solution until it won't dissolve anymore. Then you evaporate all the water and you measure the mass of solid that remains. So for example, here was the mass of the empty beaker. We filled it with water, 10 mils of water. And then we added potassium nitrate until no more would dissolve. So we had a saturated solution. And then we removed all the water, and here's the final mass. So started at 92.74, finished at 93.99. If you subtract those, you get 1.25 grams. So that would be the mass of KNO3 solid that dissolved. So you need to calculate the other 3 masses at these 3 temperatures. Okay, once you've calculated those, then we're going to graph the data. So what's that going to look like? Okay, I'm going to show you. Come on, there we go. Okay, so here's the graph that's provided to you. You are going to put temperature along the bottom. So I'm going to just start to set this up. And it's going to go 0 and 10 degrees Celsius increments. 30, 40, 50, 60, 70. We'll stop there. And solubility up the side. And this is going to be grams per 10 mil. Grams per 10 mil. And our solubilities are going to go from 0 up to about 8. 1, 2, 3. Oh my gosh, that is illegible. Let's try it again. Slow down. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so there's my axis labeled. And I'm going to graph that first data point. So that was the water was at 0 degrees Celsius right here. and there was 1.25 grams. Okay, there's my first data point. Now you are going to have 3 more data points from these 3 masses that you are going to calculate. So I'm going to pretend that I have some numbers and graph them just so you can see what the graph might look like. Okay, so we're going to pretend that at 12.5 degrees Celsius, that mass dissolved, and at 23 degrees Celsius, that mass dissolved, and at 41.5, that mass dissolved. Okay, then you have to do a line of best fit. So you're going to take a ruler and draw a straight line that gets as close as it can to those data points. So something like that. You can see if I zoom in that I pretty close to those 4 points, and I didn't use a ruler because I can't on this screen, but a line of best fit, trying to hit all 4 of those. Okay, then what you're going to do is I want you to estimate what is the solubility at 30 degrees Celsius and 60 degrees Celsius. So if this was correct, my graph, I would look at 30 degrees Celsius and I would read straight up 30 degrees Celsius till I hit the line. Oh, it did not draw that in for me. Okay. And then where I hit the line, I would read across, and it looks like it's about 6.5 grams per 10 mil. So that would be the predicted solubility at 30 degrees Celsius. Now at 60, we have a bit of a problem because my graph hasn't gone far enough, so I need to extrapolate, extend the line. Okay, 60 degrees Celsius is right here. That's where it hits and comes across 10. Looks like it's going to be 10.5. Now my graph is not the correct data points. Yours will be different per 10 mil. Okay, so what you're going to do for your assignment today is create this graph. You are going to do these 2 predicted values. Then you are going to snap a photo of this graph and send it to me as a PDF. So when I say a photo, a PDF image of your graph with your 2 predicted values. And let's throw a title on this too. So I might like you to put a title on your graph. Make sure you've labeled the axes correctly. You've shown me your 2 predictions on the graph using these lines. Yours will be neater than mine because you don't have to write on a sucky, oh my gosh, a really slow digital screen like I do. So that's your assignment. Create the graph, do the 2 predicted solubilities at those 2 temperatures. Make sure it's neat. Send the image in to me. I'll put this out as an assignment in Google Classroom for you. And then there are some questions to do as well. And those questions are, let's go with, since you're doing that graph, let's just go with numbers 1 to 5. Yeah, just page 200. And if you're in Kelly's class, page 204. And we'll save this for another day. Oh my gosh, I'm writing in Greek here. This is so slow. A-N-O-T. I have to restart this Chromebook or something because it is just painful. Okay, so this is what I would like you to work on. That is less priority though than the graph. I want to make sure you get the graph done and the predictions done and hand it in to me today. Okay? All right, have a good day, everybody, and I will see you guys tomorrow.